Welcome to this week's summary on logarithms. Today we'll be going over the relationship between powers, exponential powers, and logarithms, and some of the rules for using logs, not wooden ones. So from last time we saw that say we take powers, say 2 to the 4, that's 2 times 2, 4 times. This time we answer a different question. We ask, to what power do we raise 2 to get 16? So obviously we know it's 4 for this case, but in general we seek to solve 2 to the x is equal to 16, and we write x is equal to log to the base 2 of 16. In which case, we know the answer when we solve this, the answer is actually 4. The general case, if we have some base to some power that is equal to some answer, this is equivalent to that x is equal to, the solution is log to the base b of that value y. So let's do a couple of basic examples that we did in class. Three to the 3 is equal to 3 times 3 times 3, that's 27. And so that means that log to the base 3 of 27 is equal to 3. And which is which? This base is this base of that power, and this 3, the solution, is that one. I deliberately picked the same ones just so that we were sure which is which. Similarly, 10 to the 1 is equal to 10, and log to the base 10 of 10 is equal to 1. And again, let's just match up that the base corresponds to the base, and this value is that one. So in general, we tend to pass from the specific to the general for any base b, and we need it to be non-negative. The first power is b, and the 0th power is 1. Of course, you knew that b to the k is equal to b to the k, and so log to the base b of b to the k is equal to k. So if we did a couple of examples, the solutions of log to the 5, base 5 of 125 is 3, because 5 times 5 times 5 is 125. Log to the base 81 of 3 is equal to, well, what's the power of 3, of 81 that gets to 3? And that's a quarter, because 81 to the 1/4 is equal to 3 to the 4th to the 1/4 is equal to 3. And log to the base 8 of 1/8 is, here 1/8 is 8 inverse, multiplicative inverse, so this has to be minus 1. So now we discuss some of the general rules for logarithms. We're going to be a little bit more abstract here. So let x is equal to a to the n, and when we say this for a bigger than 0, and y is equal to a to the m, therefore we have that n is equal to log to the base a of x, and m is equal to log to the base a of y. Note that, observe, x times y is equal to a to the n times a to the m, and is equal to a to the n plus m, and therefore n plus m, which is the power of the base a, is equal to log to the a of xy. But n plus m is also equal to n plus m, which from here and from here is equal to log a x plus log a y. So here that what we've shown is that in general the logarithm of a product is the sum of the logs. Similarly, if we take x to the k, which is a to the n to the k, which is equal to a to the nk, this implies that nk is equal to log to the base a of x to the k. But nk itself, again using the same trick, is n times k, and n times k is, because n is log to the base a of x, is k times log to the base a of x. And what we observe is that this power comes out of the log. In words. For the inverse, so multiplicative inverses, observe that x over y is equal to a to the n over a to the m, and that's a to the n minus m. So similarly, log to the base a of x over y is equal to n minus m, and is equal to log to the a x minus log to the a y. We could have done this by combining the two above and using a negative power. So how do we manipulate logs? A couple more examples. One, if I lazily write log 5 plus log 3 is equal to log 5 times 3 is equal to log 15. I'm being a bit lazy here. We're going to assume that all these bases are the same base, and just happen to be unspecified. Think of it just as notation. For you, it's best if you actually write down the base. So for instance, warning, if you use different bases, you don't get the same answer. So consider log to the base 4 of 5 plus log to the base 2 of 3. Since 2 to the 2x is equal to 4 to the x, and if we set that equal to 5, we have that if we take log to the base 2 of both sides, this says that log to the base 4 of 5 is equal to x. What we get is that 2x log to the base 2 of 2, which is just 1, is equal to log to the base 2 of 5, and therefore x is equal to 1/2 log to the base 2 of 5, which is also known as log to the base 2 of the square root of 5. If we put this way over here, this means that this is equal to log to the base 2 of root 5 plus log to the base 2 of 3, and that's equal to log to the base 2 of 3 root 5, which very much isn't log to the base 2 of 15. But that's because the two logs had different bases here and here. As a second example, 2 log 3 minus 3 log 2 is equal to log 3 squared minus log 2 cubed, and is equal to log of 3 squared over 2 cubed, and that's just equal to log of 9 over 8. Again, assuming that the bases here are the same. So we got to this at the end of the class, and we're going to solve some equations. So these are slightly more complicated logarithmic equations. So it's problem 1, solve 3 to the x is equal to 5. Now you can pick whatever base you like when you take logs, but often it's easiest to pick the same base. For an unspecified base, or you would have log of 3x is equal to log of 5, and therefore x times log 3 is equal to log 5, and therefore x is equal to log 5 over log 3. And in the case that the base was 3, remember that log to the base 3 of 3 is 1, and so you just get log to the base 3 of 5. So let's try and solve something a little bit more complicated. 3 to the x is equal to, say, 5 to the x minus 2. Again, you can take logs with some, let me specify the base now as some base b. The reason people stop writing these bases is because it's understood to always be the same thing. So if I collect the x terms, if you like, you can just stop here, or you can cancel off the minus sign and swap these two around, just to multiply both sides by -1. And that's it.